My name is Kamel Bouhara, and today I'm going to introduce you to RAUC and how to get started with RAUC. So first, let me introduce myself and my company, Buildroot. We are mainly providing embedded Linux expertise in many areas like bootloader, Linux kernel, Yocto Project, and Buildroot. We also provide complete Linux BSP development, and we have a strong open source focus. When it comes to upstreaming and contribution. Personally, I have a good experience in board bring up with NXP socks, and I have some small contribution to Yocto Project and Buildroot and Linux. So, what is this talk about? This talk is just a short introduction to RAUC. The idea behind this talk is to give you a better idea of what needs to be done and how it needs to be done when it comes to integrating RAUC to popular build system like Yocto, Buildroot, but also bootloaders like U-Boot and Barebox. And hopefully I will share with you, and hopefully I will avoid you some pitfalls by sharing my own experience. So, what is RAUC? RAUC is an update system mechanism. There is a lot of many others update system mechanism like Buildout and software update. This one is developed by Buildroot, which also developed Barebox and PTXDist, and it's licensed under NGPL. So some of the RAUC features or key features you may look for. The atomicity is one of those. This is typically meaning that when your update process starts, it will either result in a valid update or complete or fully invalid update, even though your update is being interrupted, or if the image that is being installed is corrupt, or if the target is not compatible with the image. There is also security aspects. You can sign your image with OpenSSL or with an hardware secure module. And finally, you will also be able to completely customize your update scenario using bundle handles. So let's dig into what is a bundle artifact first, because this is really the central piece of RAUC update system. So typically here we have a bundle representation. So it's a signed squash file in which you will find multiple image embedded. So you can have a root file system embedded in your bundle. You can have your application. You can have files related to boot, like your kernel image or the device tree embedded in the bundle. And you also will have the manifest file that will describe all those images and how they should be handled by RAUC at the installation or the update time. So here we find two sections, the update section and the image, but there is a lot of other sections that are provided by RAUC to describe image and slots. Typically the update section is the main section in which you describe your target compatible and the version that will match your bundle version. And there is also the ability to define some options to customize your update behavior, like the install same options here that I give, that will allow you to decide whether or not to update the slot if a checksum based on the checksum value. So let's start by describing what needs to be done to integrate RAUC with build systems, and let's first start with the Yocto integration here. We have a layer, RAUC layer that is provided, and in this layer we will typically have a generic class to generate bundles, and also a lot of useful stuff like the kernel configuration required by RAUC that will enable SquashFS support. You will also find of course the RAUC package itself that is actually split in two recipes. The recipes for the host to install the host tool that is used for the bundle generation, and the recipe to install the RAUC tool on the target that is used to manage your bundle installation. And you also will be interested in the ability that the package provides to support boot scripts for sys5init and systemd. So when we start with RAUC here, we will typically start by integrating the RAUC layer in our bitbake in our layer configuration, and then we will extend the RAUC recipes to use our own RAUC configuration, to define our own RAUC configuration. Sometimes you also will be interested in using reconfiguring RAUC so that you can, for instance, install only the RAUC tool itself in your image, which can be useful when you have initramfs based update in an asymmetric scenario. We'll see later how to do that. So the next step is to create a bundle recipe. So this is the place where we describe what we will find later in the manifest file. We will here we define the target that is compatible with our image. Here in this example, I have only one slot defined, but of course you can add as slots as you need. You can have typically an application slot or a boot file system slot, like we saw before. And for each slot, you can define the file system format you want to your slot is using. And finally, you also may want to define the key you use to sign your bundle. So we are almost done here because we just need to install RAUC on the target, on the image here, and we will be able then to generate a bundle for the image we described before, and then we can install, and once the bundle is installed, we need to mark it as good here. That's the command that will be used. RAUC statue mark good is the command that will be typically launched in a boot script to validate the boot once the update is done. So now let's see with Buildroot how to integrate RAUC with Buildroot. We start by enabling the package in our build configuration. RAUC is being supported since Buildroot. I guess it was 2008 and 10, if I'm right. And if when you enable the package, you will also actually have some default option enabled, like the squashifs. And if you're using U-Boot, you will have the U-Boot firmware utils enabled, so you don't need to enable them. They are automatically selected. So the next step is deploying RAUC required files here using the root file system overlay option of Buildroot. So we can deploy all the files we need for the RAUC so RAUC can work on our target. And after we've done with the deployment, we can generate the bundle. So here in Buildroot, we will use the post image script. So the script itself can be like that. In this example, we will create a manifest file, and we will call the RAUC on the host, directly on the host, to generate our bundle. So let's see now how to integrate RAUC with bootloaders. And first, I have listed some prerequisites that you may be interested in. So, as I started integrating RAUC on Barebox, I first made sure that I had a non-volatile memory. In my case, it was an EEPROM memory, and on this EEPROM, I made sure that there is at least 200 kilobytes of space that will not be updated or touched by the application or anything else, because this is the place, the location that will be used later by the Barebox state framework to store the variables needed for the RAUC management. And you also need here the DT utils that is used by the Barebox state on from kernel users, from kernel runtime. So to start with Barebox, we need to enable first some option here. We need to enable the state framework, the state driver, and the boot chooser. So the boot chooser is the algorithm that is implemented in Barebox, and it's a generic way to manage boot targets on your embedded system. So it is typically where you will define all the boot that you have for your target. For instance, you can boot from NFS or from an AND flash or a NOR flash or even an eMMC. All those boot targets will be managed by the boot chooser, and you can define, of course, a priority or a boot order for each of these boot targets. After that, you also have the state framework that will allow you to store a set of variables. It is used by RAUC to store all the boots, the slots status after an update, and it is typically this is why you need to make sure that this storage location is not touched by the application or by any other software than RAUC. Here we have a typical we have a typical example of update scenario. Using boot chooser, we will define all the default variables required by RAUC. The behavior that will the behavior of the update mechanism is also defined by the boot chooser variables. So make sure that you dig in the boot chooser documentation to correctly set those variables at their default states. And typically, one important thing to note is that you need to make sure that the state prefix variable match the barebox device tree state prefix entry you have defined. Otherwise, your RAUC update will just fail. So now with U-Boot, it is slightly the same prerequisite. You also need a non-volatile memory, and you will also have to install some user space tools. Here it's firmware utils, and you will have to define a location for the U-Boot environment variables, so that RAUC can access them from the user space to update its slot, the slots counters and the boot order that we will see later. And you may also want to use some U-Boot options to define where to store the environment variable. And if you wish to update U-Boot in your update scenario, then you may also need to define a redundant environment, a copy of your environment on your storage video. So when it comes to U-Boot, you will typically start by looking in the boot script that is provided by RAUC in the RAUC repository. This is an example of update scenario, a symmetric update scenario, in which you will retrieve the variables I've talked about before. So there is 3 variables. So it's typically for it fits basic scenario, but if you need to more variables to update your application, for instance, then you may need to modify RAUC and how the RAUC is using those variables directly from the RAUC code source and the boot chooser interface that is provided by RAUC. But here, for those variables, it's quite simple to understand. You have the boot order and the counters that will be used to attempt to boot on each each defined slot. Once you have integrated the boot script, you are ready to load it and run it at each boot, at each of your system boot. So here it's an example with an MMC storage. So now let's see some update scenarios we can implement with RAUC. The first one is the asymmetric update. This is typically a good solution for device with minimal storage resource. So here typically we have a rescue system in which we will boot. So we can imagine that we are on the main system. We want to boot on the rescue system, then we will use the RAUC mark status to reboot on the rescue system, and then from the rescue system we can update the root file system based on typical based on USB or a local storage or even the network if we want. But what you need to note is that this is a scenario where there is no fallback possible. If your main system is not updated correctly, then you need to make sure that you have a fallback scenario that will be implemented by your that will be executed from your rescue system. And also you will need several boots to achieve your update from a rescue system. Here we have a typical example of script that can be run from the initramfs from the rescue system. So just some little things to note. I have to update to make sure that the clock is well synchronized, because the RAUC verification steps when installing the bundle is based on the certification date, and if your clock is not synchronized, then it may fail, like in this example. And of course, you need to manually change the active boot slot here to be able to boot on your main system. Now with the redundant symmetric system update, some little things here to note is the use of the parent property in the slot sections. So we saw that there is a lot of options that can be used in the manifest file to customize the behavior of the updates. The parent property here is one of them. It allows to bind multiple images together in the same bundle update. So when you update the boot file system, you make sure that the boot file system will be updated at the same time, so you don't end up with a system with heterogeneous with different with different image. So depending on the application, of course, it can be complex to update all your images, and you may need to fully take advantage of the RAUC post-install script or RAUC bundle handlers features. So we saw that from both Yocto and Buildroot, RAUC is fully supported. We have, of course, good integration in Barebox, because it's developed by Penguintronics, and this is the same vault that developed Barebox and RAUC. Typically, you don't have to deal with environment variables when you work with Barebox and RAUC. But with U-Boot, it's very easy to start with the boot scripts example we saw in a simple symmetric update scenario. If you need something more complicated or more difficult, you may need to dig into the RAUC code and how to modify the boot chooser interface. And you will also have to make sure that your device, before starting your project, that your device is well sized for your update strategy, and that your application requirement fits with the RAUC features. So typically, if you're willing to use dbus, RAUC will just fit well with your application requirement. And finally, there is the RAUC is a very good, is very well maintained, and in its last version, you will find support for secure boots with the VT format support. So I really recommend you to start by reading the RAUC documentation, because it's a very good documentation, and you will find almost everything you need. So that's it. I hope that I give you all the information you need to start with RAUC, and I hope to see you soon. Goodbye.